Right. Consider this case, all of you. This is basically a Wheatstone bridge of capacitors. We had discussed how to deal with a Wheatstone bridge in case of resistors. In case of capacitors also, you do the same thing. If the ratio of capacitances on one side is same as the ratio of capacitances on the other side, okay, 1 by 2, 2 by 4 is also like 1 is to 2, then the fifth capacitor, the one in between, can be ignored. What do we mean by ignoring that fifth capacitor? You can completely remove it. Okay. You can consider the circuit like this, or you can replace it with a wire also and find out the overall capacitance or effective capacitance across the ends. Okay, that is when the Wheatstone bridge is balanced. If the ratio on the left side is same as the ratio on the right side. But how to deal with it if it is unbalanced? Let us see. Let's say you have C and 2C, and you have 2C and C on the other side, with some, okay, let's say C in between. What you need to find out here is the effective capacitance of this system between the ends. Okay. Uh, if any of you remember, you can tell me, how do we deal with unbalanced Wheatstone bridges of resistors? How do we find out the effective resistance of an unbalanced Wheatstone bridge of resistors? Uh, what did you say? It was not clear.
KCL, KVL.
We assume that network is connected to a cell. You can take a cell of any EMF. You can even take a cell of some unknown EMF V, no problem. Or take it to be of some known EMF, 10 volts, and apply KCL, KVL, find out the net current in this circuit. Then effective voltage divided by net current gives us the effective resistance. Okay, if it's an unbalanced Wheatstone bridge, that's how we deal with it. You do the same here also. You are given the capacitances, but you see that it's an unbalanced Wheatstone bridge of capacitors. So what you now have to do is assume it is connected to a cell. You can assign any EMF to the cell. For now, let's call it as V. Okay, or you can call it E also, not an issue. What we have to find out now is how much charge flows through the cell. If you know how much charge flows through the cell when the cell's EMF is E, then you can use Q is equal to C effective multiplied with E. And you get effective capacitance by charge flown divided by the EMF of the cell by using this. Okay. Now, in order to find out the total charge flown through the cell, you will have to apply KVL. Okay. KVL, KCL to this loop also. I mean, to this circuit also. Now, to apply KVL, you need to know how to express the potential change across resistors, batteries, and capacitors. Across resistors and batteries, we have already discussed. Suppose current is flowing this way. If you move in the direction of current, the potential change across a resistor is minus IR. Opposite to direction of current, it is plus IR. Then for a cell also we discussed, if you are going from positive terminal to negative terminal, it is minus E, negative to positive, it is plus E. Let's see how to express potential change across a capacitor so that we can use KVL in case of capacitors also. We'll solve some other problems also based on this. Consider a capacitor like this. Now, I told you this is the standard symbol for a capacitor. It doesn't necessarily have to be a parallel plate capacitor. For any capacitor, this is the circuit symbol we use. Let's say its capacitance is C, and assume this plate has a charge plus Q. This plate has a charge minus Q. Okay. Now, the potential difference across the plates or between the plates of a capacitor is Q by C. Q is equal to CV, V is equal to Q by C. But when applying KVL, You move along a closed path in a circuit. Okay. And while moving in that closed path, you may go from positive plate of the capacitor to the negative plate. In that case, the change in potential will be negative. You are going from positive to negative means you are going from high potential to low potential. Then delta V has to be written minus Q by C. And if you go from negative plate to positive plate, low potential to high potential, then the change in potential across the capacitor will be written plus Q by C. But many times, you wouldn't know which plate is positively charged, which plate is negatively charged. In fact, many times you will be asked to find out what is the charge on the capacitor. Then, how exactly to write potential change across a capacitor? You can uh, you can have a general formula for potential change across a capacitor. Now you see, when going from left to right, the first charge you come across is plus C, sorry, plus Q. Okay. So you can write this as negative of plus Q divided by C. When going from right to left, the charge on the first plate you come across is minus Q, and you can write this as minus of minus Q divided by C. The plus Q here and the minus Q here in this case are the charges on the first plate that you come across when moving across a capacitor. So delta V across a capacitor or when moving from one plate to the other plate of a capacitor can always be calculated as negative of charge on the first plate divided by C. This formula, okay, can be used to express the change in potential across a capacitor while applying KVL. So negative of charge on the first plate divided by C. Okay, hope this is clear to all of you. You can make a note of this. We will apply this to solve problems involving capacitors in circuits where you have to apply KVL. Okay, let's solve a simple question based on this. Single loop. Assume this resistance is 2 ohm, this resistance is some 3 ohms. Let's say this is a 20-volt cell, this is a 10-volt cell, and capacitance is 4 microfarad. You have to find out the charge on the capacitor. And let's say the current here is flowing this way. Or, okay, current in this loop is flowing in this direction. And the current flowing is 2 ampere. Fine. Do this, all of you. Calculate charge on the capacitor. There are many ways to proceed. But let us solve it using KVL. Now, what you are asked to find out is charge on the capacitor. Can any of you tell me, by looking at the circuit, which plate of the capacitor will be positively charged? You can solve it without knowing that also, but there is a way of telling that. In this case, which plate of the capacitor is positively charged? Any idea? Think about it. I'll give you a minute. Right. That is the logic that you're supposed to use. See, these two cells, they are connected with the same orientation of their terminals. This cell will try to drive current this way. This cell also tries to drive current this way. Both of them try to drive current clockwise, but the actual current in this loop is anti-clockwise. So this capacitor should be having potential opposite to or polarity opposite to those of the cells. And in fact, its potential difference should be stronger than that of both the cells. Okay, we will prove it also. See, the cells are trying to drive the current clockwise, but the actual current is anti-clockwise. And the only one who can do that is this capacitor. because it can maintain potential difference. So how is that happening here? You have to understand that this capacitor was charged in a different circuit and placed in this circuit. Okay, these two cells 20 and 10 could not have charged this capacitor. If they had done that, there's no way current can flow in the reverse direction. So this capacitor was charged by something else, I mean some other battery, and placed in this circuit. So actually this capacitor is getting discharged now. Let it be. Even if you didn't know which plate was positively charged, you can find out. Okay, assume whatever you want. Let's assume the right plate to be positive having a charge plus Q, left plate to be negative having a charge minus Q. Let us consider it like this. Okay. Now what I want you all to do is apply KVL to this loop, because it's not a case of single cell directly connected to the battery. There are two cells. Sorry, single cell directly connected across the capacitor. There are two cells. And also, this is the capacitor which is getting discharged as we have considered. Even if you didn't know whether it is getting charged or discharged or whatever also, you can apply KVL to get the answer. I'm just telling you why you cannot directly tell in this case. You can't use Q is equal to CV because we don't know the potential difference across the capacitor. Okay, there's a way of telling that also. Anyway, let's apply KVL first. So I want you all to start from this point and move this way clockwise so that we all write the same equation and check whether we have made any mistakes. So write the KVL equation, all of you. I'll give you a minute. And try to find out the charge on the capacitor also. I told you, when moving from one plate of capacitor to another, the potential change is given by the formula negative of charge on the first plate that you come across divided by C. Okay, across resistors and cells, you already know how to write potential changes. So make use of that and write KVL equation for this loop. Any answer for charge? Okay. Pawan, can you unmute? Vanilla, can you unmute?
Yes, sir.
Huh. So tell me the KVL equation that you have written for this loop.
So minus 2
Minus?
minus 2 I say.
I is given as 2 amperes, no? But
Minus 4, sir.
but why minus? Which way is current flowing in that resistor? To the left or to the right?
To the left, sir.
You are moving to the right, means you are moving opposite to current. When you are going opposite to current, you should take plus IR. Okay, so it will be plus 4. Ah, Continue moving along this loop. You go from one side of the capacitor, one plate of the capacitor to the other plate. In that case, how do you write the potential change? Negative of charge on the first plate divided by C. We'll keep it as C for now. We'll substitute as 4 microfarad later. We assume the left plate is negative. Negative of negative becomes positive. Okay. Or according to our assumption, we are going from negative plate to positive plate, means we are going from low potential to high potential. So you should write plus Q by C. If Q is actually as assumed, it will come out positive. If Q is a reverse of what we assumed, it will come out negative. Okay. Vanilla, continue. When you go from negative terminal of the cell to the positive terminal, how much potential change do you consider?
Plus 20, sir.
Plus 20. Okay. And continue moving along this loop. 3 ohm resistance. Are you going in the direction of current or opposite to it?
Opposite, sir. So
Opposite.
6.
So plus 6 plus IR, that becomes 6. And again, 10-volt cell also, we are going from negative terminal to positive terminal. So plus 10. That's all. And we return to the starting point. This sum should be equal to 0. That is how we apply KVL. Okay, 20, 10, 30, 6, 4 is another 10, 40. So Q by C is equal to minus 40. You get Q as minus 40 into C is 4 microfarad. So charge becomes minus 160 microcoulombs. And why we got a negative answer means the sign of charge we took is wrong. Okay. And we knew that already. Left plate is positively charged, right plate is negatively charged. So the charge on the left plate is 160 microcoulomb. The charge on the right plate is minus 160 microcoulomb at this instant. And once you know charge on a capacitor and its capacitance also, you can even tell potential difference across the capacitor. Q by C. 160 microcoulomb divided by capacitance is 4 microcoulomb. It has a potential difference of 40 volts. That is why it is able to drive current opposite to these two batteries. Okay. So it was charged using some other cell or some other circuit and placed in this circuit. It is dominating the other batteries also. Fine. So this is how you use, or this is how you apply KVL involving, in circuits involving capacitors. Or this is how you write potential change across a capacitor. You assume some charge on the plates, and as you move from one plate to the other or one side to the other, the potential change is expressed as negative of charge on the first plate divided by C. Okay. Now let us come back to this unbalanced Wheatstone bridge of capacitors. This is the main thing that we wanted to discuss actually. How to find out effective capacitance of an unbalanced Wheatstone bridge of capacitors. As I said, the idea is same. You'll have to apply KCL, KVL, like how we did in case of unbalanced Wheatstone bridge of resistors. How to begin? In Wheatstone bridge of resistors, what do? We assume some current here and we split the current into two branches. Here, you will have to do that in terms of charge. Let's say the total charge flowing through the cell in charging this capacitance network is Q. Now we will have to split Q. Okay. For convenience, instead of using Q1, Q2, those 1, 2 symbols, I'll use ABC symbols. Let's say the total charge flowing, let it be Q itself. Assume some charge A gets deposited on this capacitor. Then Q minus A will get deposited here. Okay. And on the other side, the 2C which is above, let's say it has a charge B on this plate. Okay. Now there is an isolated region here. Now if A gets deposited here, minus A will get deposited here. And if this is B, then on the third plate, can any of you tell in that isolated region, on one plate we have taken charge minus A, on the other plate we have taken charge B, both of which are unknowns. How much will be the charge on the third plate of that isolated region? Assuming isolated region is neutral.
So A minus B.
Correct. It will be A minus B, such that the total charge on that isolated region is 0. That's all. That is what we mean by isolated region being neutral. And if that charge is A minus B, this charge will be B minus A. Okay. Now you see one more. Fine. On the 2C capacitor, if this is B, this will be minus B. If this is Q minus A, this will be A minus Q. Okay. Now there's one more isolated region here. We know charge on two plates of that isolated region. Tell me the charge on the third plate quickly.
B minus Q.
B. Can you repeat?
Q minus B.
It will be Q minus B. See, the sum of these already existing charges, B minus A plus A minus Q, is B minus Q. Opposite of that should be on that other plate such that net charge becomes 0 in that isolated region. So on that plate, it will be Q minus B. Then here it will be B minus Q. We have distributed the charges. Like in case of unbalanced Wheatstone bridge of resistors, what we do is we distribute currents. We assume some EMF here. We take main current to be I. We split the current. Some current A flows this way, then I minus A flows this way. Some current B flows this way, then A minus B will flow this way. A minus B and I minus A combine. I minus B flows this way. Then we apply KCL, KVL. KCL we have already applied. Then we apply KVL. We are doing something similar in capacitors. We distribute charges here, not currents. Okay, we assume this system is fully charged. When fully charged, let's say these are the charges on it. Okay. Now apply KVL for, okay, what are the unknowns here? Q is unknown, A is unknown, B is unknown. Capacitances are given to us. Okay. Those C, 2C, those are known to us. And this EMF also, we assume it's a known EMF. We will get charge Q in terms of E. And then what is our aim? Our aim finally is to write it this way. Total charge flown through the cell is effective capacitance multiplied with its EMF. So how do you get effective capacitance? Q divided by EMF. Okay. So you can keep it as E if you want. Otherwise, you can assign a numerical value also, 10 volt, 20 volt, 1 volt. Any numerical value also you can take. You will get Q in terms of E. And then that ratio will become independent of E. Okay, let's write it in terms of E itself. You'll understand that it doesn't matter what you take it as. So I want you all to apply KVL carefully. I'll tell you which loops to apply it to. One loop, you take this one and move this way. Other loop, second loop, you take this one and move this way. We have already assigned the charges and you know how to write potential change across a capacitor. So two loops like this. And the third loop, you take this outermost loop and move this way. Okay. I want all of you to write KVL equations in this same manner so that we can check whether we have done correctly or not. So loop 1, loop 2, loop 3. If you write KVL equations, you will get three equations involving charges A, B, and Q. Then you'll have to solve those equations for Q. Means you have to eliminate A and B from the equations. And then Q by E will give you the effective capacitance. So do this carefully. I'll give you all 3 minutes exactly. Try to find out effective capacitance. Okay, Hemant, can you tell me KVL equation for the first loop?
Yes, sir.
Hmm.
Minus A by C.
Negative of, see, when we move across or when we move along this loop, the first plate we come across is this charge on it is A, so minus A by C.
Then B minus A by C.
Negative of A minus B divided by C, you can write it as B minus A by C.
And then plus Q minus A by 2C.
Okay, negative of A minus Q, that is Q minus A divided by 2C, and you return to the starting point. So this should be equal to 0. If any of you have any doubts in this, you can ask. Fine. Second loop, the first plate we come across is this having a charge B, so minus B by C, and continue moving. Then we come across B minus Q. Negative of B minus Q, I'm writing it as Q minus B. Okay, wait. The first capacitor had capacitance 2C. So minus B by 2C. Then B minus Q. So negative of B minus Q is Q minus B. Its capacitance is C. And continue moving along the loop. The next charge you come across is B minus A. Negative of that will be A minus B. So A minus B divided by C should be 0. Okay. Now the outermost loop. Move this way. The first charge we come across is A, so minus A by C. Capacitance is C. Then this, the charge we come across is B, so minus B by its capacitance is 2C. That's all. And then the cell, you go from negative terminal to positive terminal of the cell. So plus E, and you return to the starting point. So plus E is equal to 0. We need to solve these equations now and get Q in terms of E. Okay. Now, in the first equation, for the first loop, whatever we wrote, that C can be sent to the other side, it will get cancelled. LCM, you have to take 2, then it becomes minus 2A plus 2B minus 2A plus Q minus A is equal to 0. I took LCM 2. So effectively, what does this become? Minus 5A plus 2B plus Q is 0. Next, for the second loop, minus B plus 2Q minus 2B plus 2A minus 2B is equal to 0. I took LCM 2 and sent the C to the other side. Then effectively it becomes minus 5B, okay, plus 2A, okay, plus 2Q is equal to 0. Fine. And then the third loop, take LCM 2C, minus 2A minus B plus 2CE is equal to 0. Okay. We have to solve these three equations now. We'll eliminate variables one by one. What can we do? From the third equation, let us take B. B is equal to 2CE minus 2A. We'll put that in the first two equations. Then the first equation changes to minus 5A plus 2 times of B. 2 times of B becomes 4CE minus 4A plus Q is equal to 0. And the second equation becomes minus 5B, that becomes minus 10CE plus 10A. Okay, minus 5B, yes, plus 2A plus 2Q is equal to 0. So in one equation we have, like in the first equation, minus 5A minus 4A, that is minus 9A plus Q plus 4CE is equal to 0. And in that second equation, 12A plus 2Q minus 10CE is equal to 0. Okay. 9 and 12, what can we do? We can multiply the first equation with 4, second equation with 3 and add them. First equation, if you multiply with 4, minus 36A plus 4Q plus 16CE is equal to 0. Second equation, you multiply with 3, 36A plus 6Q minus 30CE is equal to 0. Add these equations now. 4 plus 6, 10Q minus 14CE is equal to 0. So you get 5Q is equal to 7CE. That means Q by E is 7C by 5. And that becomes the effective capacitance of this network. Anyway, you do the solution once again, but this is how you deal with an unbalanced Wheatstone bridge of capacitors. Okay, assign charges. There will be, if it's a Wheatstone bridge, there will be 3 unknown charges. The main charge or the total charge. And in the distribution, there will be 2 more unknowns, A and B. Okay, we applied KCL while distributing the charges itself. And then we applied KVL for 3 loops of this network. And solving those equations gave us the effective capacitance. Okay. Now consider this case, a simple case of capacitors connected one next to another. Let's assign capacitances also. Let's say this is 2 microfarad and this is 1. Uh, they're in series, no? And let's take it as 6 and 3. 6 microfarad, 3 microfarad. Let's say they are connected to a cell. Cell EMF, let it be some, let's take some 2 volts. Right. A series combination of capacitors connected to a cell. Tell me the charge and energy on each capacitor. Can any of you tell this directly without using pen and paper? Simple, 2 capacitors in series, voltage is given to you. Charge and energy stored in each capacitor. Okay. Practice more questions. It's quite easy actually. When capacitors are in series, the charge on each of them will be same. Q is equal to CV. V is equal to Q by C. If Q is same on both of them, V, the potential difference across each one of them, will be inverse or will be inversely proportional to the capacitance. So distribution of voltage will be in the ratio 1 by 6 is to 1 by 3. That means 3 is to 6 means 1 is to 2. You have to divide 2 volts in the ratio 1 is to 2. How do you do that? 2V by 3 or 2 by 3 volts here and 4 by 3 volts here. Those are the potential differences that they get. And once you know potential differences, you can directly tell the charge Q is equal to CV. So for the first one, 6 microfarad multiplied with 2 by 3. 6 into 2 by 3 becomes 9 microcoulombs. Wait, 6 into 2 by 3 is 4 microcoulombs, not 9. Hmm. So 4 microcoulomb is the charge on the first capacitor. Next, 3 into 4 by 3, again 4 microcoulomb charge on the second capacitor. Okay, I didn't have to calculate that. They will get equal charge anyway. They are in series. These are the charges. And if you want energies, you can use half CV square, you can use Q square by 2C, any one of them. And the answer will be in microjoules. Fine.
Like
Can one
what?
of you,
Can you tell how the division of volts that you took?
did you understand that it should be divided in the ratio 2 is to 1, 1 is to 2?
Because it is inversely proportional to voltage.
Inversely proportional to capacitance. V1 will be Q divided by C1 and voltage across the second one will be Q divided by C2. So the ratio in which you give the voltages is 1 by C1 is to 1 by C2. That is 1 by 6 is to 1 by 3, which is 1 is to 2. Okay.
Yes, sir.
Applied voltage was 2 volts. I split it in the ratio 1 is to 2. Then it becomes 2 by 3 and 4 by 3.
Got it, sir.
Okay. Can any of you tell me when this is valid? When is it valid to assume that the charges on the capacitors are equal? This is valid only when isolated regions are neutral. Okay. When we discussed combination of capacitors, that's the first thing I told you. If isolated regions are neutral, then only you will get charges like this. Minus Q on one plus Q on the next one. Again, minus Q on one plus Q on the next one. Okay, it's important to keep that point in mind. Now let's see what to do if the isolated region is not neutral. Then obviously the charge won't be like this. Now what we found out here is that this plate has plus 4 microcoulomb charge. This plate has minus 4 microcoulomb charge. And then again, this plate has plus 4 microcoulomb charge. This plate has minus 4 microcoulomb charge. That is what we found. And the net charge here is 0. We already made use of that. Under the condition that isolated regions are neutral only, you can use that effective capacitance formula also. Okay. What if isolated regions are not neutral? Let us take this same network and give some charge to the isolated region. How much charge? Let's say the isolated region had its own charge of plus 2 microcoulomb. And now we connect it to this battery, connect this network to this battery. The question is again the same, find out charge on capacitors and energy stored in the capacitors. No, how will you do? Any idea, anyone? Okay. Basic approach. Assume charge on one of the plates as Q. Fine. Now each plate has two surfaces. Charge on which surface should be assumed Q? See, this is the isolated region here, and that isolated region had a charge plus 2 microcoulombs. Okay. Let's say charge on the inner face is Q here. Then it has to be minus Q here. There is no other choice. The flux emerging from one plate should terminate on the other plate because these are conductors. So on the inner surface, if you assume the charge to be Q, then on the inner surface here it has to be minus Q. Now where will that minus Q come from? Induced charge. This plus Q, you can say, is being delivered by the battery from the other side. That plus Q will attract this minus Q. So we call it as induced charge. Fine. If a minus Q is appearing here, then the remaining charge in this region, isolated region, is 2 plus Q. 2 microcoulombs plus Q. That 2 microcoulombs plus Q will have to appear on the other side. So the charge here will be Q plus 2. 2 is in microcoulombs, so we'll get answer for Q also in microcoulombs itself. And if that is Q plus 2, then this should be minus Q minus 2. But this is not possible. I mean, you can't stop here because this part of the circuit, okay, other than the isolated region, this part was neutral. Now, what did we do to the leftmost plate? We assumed a charge, it has a charge small q here on the, we gave charge small q to the leftmost plate and the rightmost plate is getting minus q minus 2. Then what is the net charge on this region now? Minus 2. How is that possible? Net charge on this region was 0. So it can't have minus 2. Then in such cases, okay, where isolated regions are not neutral, what happens is, see, you distribute charge like this, but you have to ensure that whichever part was neutral remains neutral. Okay, there's no jumping of charge that can happen. Okay, the neutral part has to remain neutral. How do we keep it neutral? What is missing here? This remaining part of the circuit has a charge, excess charge minus Q. Then there should be another charge plus, sorry, what am I saying? This remaining part of the circuit, which was neutral, is now having an excess charge minus 2. So we should give it a plus 2 somehow. And how do we do that? We had discussed this before also. If there are a set of plates, set of parallel plates, identical parallel plates. Arranged like this. Let's say one had zero charge. Let's say the other had a charge of 2 microcoulombs or coulombs, whatever it is. Or let's say they had Q1, Q2. How do we distribute charges on the plates? I gave you a shortcut also. The net charge on this system, which is Q1 plus Q2, half of it will appear on the first phase. Then this becomes Q1 minus Q2 by 2, such that total charge on the first plate is Q1. And then this becomes Q2 minus Q1 by 2. These two should be exactly opposite to each other. And then this becomes Q2 plus Q1 by 2, such that net charge on the second plate is Q2. And you will see that the first phase and the last phase have exactly the same charge, which is half of the total charge of this system. You do the same here also. Now, the charges that we have considered here, this effective sum is 0. But the net charge on this entire system is plus 2 microcoulomb. How do you distribute that? You have to put a plus 1 microcoulomb on this plate and a plus 1 microcoulomb on this plate on the outside, not on the inside. So if isolated regions are not neutral, you will see charge on the outer side of the first and last plates. That is what happens. Had this 2 microcoulomb not been present, then this 1 microcoulomb and 1 microcoulomb also would not have been present. Then how do you get the charges? You get them like this. Simple. Q minus Q, Q minus Q, equal charges on the capacitors. But because of this 2 microcoulomb extra charge, you are getting a plus 2 here. You are getting out of, okay. The inner plate charge here becomes Q plus 2, such that total charge on that isolated region is plus 2. Then this has to become minus Q minus 2 because these two have to be equal and opposite. But where will that net charge go? It has to get split. Half here, plus 1 microcoulomb on this plate, on the outer surface of this plate, and plus 1 microcoulomb on the outer surface of this plate is what you will see. Now, look at this region of the circuit, which was originally neutral. The isolated region had a charge of 2 microcoulomb, okay, but remaining circuit was neutral. Now see the total charge on the remaining circuit. On the left side, there is Q plus 1. Right side, there is minus Q minus 2 plus 1. That is minus Q minus 1. And this side is Q plus 1. The sum becomes 0. So the remaining circuit effectively remains neutral. This is how the charges will get distributed if isolated region is not neutral. Okay. And now if you want to know how much is the energy stored in each capacitor, basic KVL you will have to apply. Or see, the first capacitor 6 microfarad, on its inner surfaces, it has a charge of Q and minus Q. That Q and minus Q only will produce the field between its plates. Okay, like this case of parallel plates, the field from here to here depends only on this charge and this charge. It doesn't depend on the charges which are outside. Okay, similarly, the field between the plates of a parallel plate capacitor or a capacitor depends on what charges are there facing each other, Q and minus Q. So the voltage across the first capacitor will be Q by C. Okay. That second capacitor also, the charges facing are Q plus 2 and minus Q minus 2. So voltage across the second capacitor will be Q plus 2 by C. Its capacitance is 3. Sum of these two should be equal to the applied voltage. So Q by 6 plus Q plus 2 by 3 should be equal to 2. You can get Q from there. And once you get Q, you can tell the potential difference and energy stored in each capacitor between its plates. So this is how you deal with series connections of capacitors in which isolated regions are not neutral. Okay. So we have discussed what to do with unbalanced Wheatstone bridge of capacitors. We have discussed what to do if isolated regions are not neutral. This is all slightly high level, important for JE advanced, I would say, because you should know how to distribute charges or how to deal with situations. For NEET and JE mains, they may not ask this deep, but it's always better to know the subject completely. One more thing we did not discuss is energy density in an electric field. Small idea only. Consider a parallel plate capacitor. Now, capacitors, as I told, are devices used to store energy, and we can quickly retrieve that energy also. So, let's say a capacitor is given charge Q, means plus Q on one plate, minus Q on the other plate. If it doesn't matter whether it's a parallel plate capacitor or any capacitor. For example, we are taking a parallel plate capacitor. Now, due to this plus Q minus Q, there will be a field between its plates. Okay. We even know how much that field is. It's like field created by two sheets. Each sheet creates sigma by 2 epsilon naught. Net field is sigma by epsilon naught, which is Q by A epsilon naught. That is the net electric field between the plates of the parallel plate capacitor. Now we know this capacitor stores energy, Q square by 2C, where capacitance is epsilon naught A by D. Okay, if dielectric is there, you know how to account for it. Fine. We even know how much energy is stored in this capacitor, half CV square or Q square by 2C. C means epsilon naught A by D. That is the energy stored in this capacitor in terms of its charge. Okay. Now, this energy is stored in the electric field between its plates. Okay. This energy is present in the electric field. Not just in case of capacitor. Anywhere, if there's an electric field present, there is energy in it. That's why when you release a charge in an electric field, it can accelerate. It gets kinetic energy. It is using the energy from the electric field. Okay. Not just electric field, gravitational fields have energy in them. Magnetic fields also have energy in them. Fine. If field is present in a certain region of space, there is energy in that space. Okay. So the energy stored in this parallel plate capacitor, Q square D by 2 epsilon naught A, is present in the electric field between its plates. Now, the electric field between its plates is spread over this volume. Okay, here on screen it looks like area, but in 3D this is a volume between the parallel plates. How much is the volume? Area of the plates multiplied with the distance between them. Now, this much energy is spread in this much volume. Then, and we know that the electric field between the plates of a parallel plate capacitor is uniform. If the electric field is uniform, the way this energy is spread will be uniform. You won't see more concentration of this energy on one side and less concentration on the other side. If field strength is same everywhere, then energy density or the distribution of energy will be same everywhere. So why we consider parallel plate capacitor as an example is because it has uniform field between its plates. But the result we derive will be applicable to any case. See, generally also, any formula we first discuss for uniform case, then if it is non-uniform, we integrate. Okay. So we are considering a uniform electric field, which we know exists between the plates of a parallel plate capacitor, and we even know how much energy is there in that electric field. Therefore, energy density, that is energy per unit volume in this electric field, is basically Q square D by, or fine, Q square D by 2 epsilon naught A. That is the energy. In how much volume is it present? AD. So energy divided by volume. D gets cancelled. It becomes Q square by 2 epsilon naught A square. Multiply and divide with epsilon naught. Why? Because we are deriving energy density in terms of, we are deriving energy density in the electric field. So it'll be better if the answer is in terms of the electric field. And electric field between the plates is Q by A epsilon naught. Now here we have Q square A square. Epsilon naught square is not there, so I'm multiplying and dividing with epsilon naught. Therefore, the energy density in that electric field becomes Q square by A square epsilon naught square into epsilon naught by 2, which is basically half epsilon naught. This term is square of the electric field, E square. This generally is the energy density in an electric field E. Wherever the field is E, the energy per unit volume will be this much. Okay. And if you know over how much volume that field is extended, you can tell what is the energy stored in that volume, in that space. Okay. Very useful idea. Simply by knowing the electric field, you can tell energy present in that space. Okay. If electric field all over that space is the same, then you can write energy in that volume is this energy density half epsilon naught E square multiplied with the volume. Okay. Generally also, we write density as mass by volume. If you want total mass of the object, density into volume. So here, if you want total energy of the, in that space, energy density multiplied with volume is what you are supposed to do. But if density is variable, how do you calculate mass? You write mass of one element first, rho into dV, and then total mass is integral of rho dV, integral of mass of each element. Similarly, if electric field varies from point to point, okay, if electric field is non-uniform, then obviously this energy density will be non-uniform. If it is non-uniform, then you will have to express energy in a small volume first. Half epsilon naught E square multiplied with dV, small volume. Then total energy will be integral of this. Okay, just note this down, all of you. We'll solve one question based on this and close the session. Right. Uh, let's solve some problems based on this. Consider two concentric spheres. Let's say a small sphere has a radius r, bigger sphere has a radius 2r. Let's give them equal and opposite charges. So plus q to the inner one, minus q to the outer one. We know how they will get distributed on concentric shells. Okay. Now these two shells will have an electric field between them, which will definitely be non-uniform. Okay. The field created by a sphere outside it is non-uniform. It's like that of a point charge, kq by x square. Non-uniform field is there, but there will be some energy stored in this system. There's a way to tell the energy directly also without using the electric field. How? See, inner radius is r, outer radius is 2r. Assume the charge given is q, plus q to one of them, minus q to the other one. You can think of this as a spherical capacitor. What is the capacitance of a spherical capacitor? 4 pi epsilon naught, assuming there is vacuum between them. 4 pi epsilon naught AB by B minus A. AB means R into 2R divided by B minus A means 2R minus R. So that becomes 8 pi epsilon naught into R. That is the capacitance of this spherical capacitor. Now for the energy part. Energy, you know the charge, so you can use Q square by 2C. That's all. So Q square by 2C means 16 pi epsilon naught R. That's the energy between these two spheres. Okay, that's the energy in this system. Now let us try to derive this by integrating the electric field. Okay. Now between these two shells, whatever field is present, electric field, this will be only due to the inner shell. Outer shell being uniformly charged cannot create a field inside itself. Okay, so whatever field arises is only due to the plus q. And you can write the expression for that field as kq by x square, where x is the distance from the center. Okay. And that field extends from where to where? It extends from x is equal to r to x is equal to 2r. It is radially directed, and with radius, the field changes. Okay. Now we know energy density in an electric field is half epsilon naught E square. So energy density here will be half epsilon naught. When you square this, it becomes k square q square by x power 4. Clearly a non-uniform energy density. Okay. We want to find out total energy using this energy density. Now this energy density varies with what? It varies with distance from the center. So what we are going to do is we are going to consider a certain volume which is equidistant from the center. A volume which is equidistant from the center will be in the form of a shell like this. Okay, this gray volume that I have considered is equidistant from the center. You can assume its radius is x and thickness is dx. Over that small thickness dx, we can assume the energy density is uniform. Then what we will do is we will write the volume of this shell. How to write volume of a shell? Area multiplied with its thickness. Now we know the energy density, we know the volume. Okay, wait, this is not U, this is U by volume. We know energy density, we know volume. Then we can tell the small energy stored in that volume, in that gray space. How much is the energy stored? Half epsilon naught k square q square by x power 4 multiplied with the volume over which that extends, 4 pi x square dx. X square x power 4, 1x square will remain. 4 pi epsilon naught is 1 by k. There's k square here, so 1k and 1 4 pi epsilon naught can be cancelled. So what remains is kq square by 2x square dx. Okay. Therefore, the total energy between the two shells, inner shell and outer shell, will be integral of this kq square by 2 integral 1 by x square dx. Integral 1 by x square is minus 1 by x. Substitute limits r to 2r. 1 by r minus 1 by 2r becomes 1 by 2r. The answer becomes kq square by 4r. And k is 1 by 4 pi epsilon naught. So q square by 16 pi epsilon naught r is the total energy between the two shells. And that is what we got before also by considering it as a capacitor. Okay. So we have just seen one application of energy density in an electric field. So if there is an electric field E anywhere, it could be uniform, it could be non-uniform. Depending on the electric field, you can tell how much is the energy density. The formula is half epsilon naught E square. Once you know energy density, multiplying it with volume can give you the total energy present in a certain space. If the energy density is uniform, directly multiply it with the entire volume. If it is non-uniform, you do it this way. In fact, using this idea, you can tell the energy of a single sphere, not a capacitor. Let's say there is a single sphere having a charge, shell only, spherical shell having a charge q spread over it. Obviously, if it's not under any external influence, it will be spread uniformly. How much field will it create outside? See, it can't create a field inside, it will create a field outside only. The field will be radially directed like this. Field created outside it will be kq by x square. That's the field. Then the energy density in that field will be half epsilon naught. Okay, we know this. Half epsilon naught into E square, k square, q square by x power 4. So basically it's this same field. Now we want to find out what is the energy of this charged sphere. Now till what distance will the field of this charged sphere extend? It will extend up to infinity. So you just have to change the limits of this integral. Same field, same volume, same elemental volume and all. Only the limits will change from starting distance r, which is the radius of the sphere, to final distance infinity. So effectively, this becomes 1 by r, and the energy of the sphere, self energy of the sphere, becomes kq square by 2r. Self energy of a shell, uniformly charged shell, is kq square by 2r. Okay, so a single charged sphere, okay, a single charged spherical shell will store this much energy, kq square by 2r. Okay, it's called the self energy of the shell. We are deriving this by making use of its electric field. Okay, and energy density in an electric field. There are other ways also to derive this, but we have done it this way. That's fine. Using this, you can tell the self energy of a solid sphere also. You can treat the solid sphere as a collection of hollow spheres. Wait, not as a collection of hollow spheres. There's another way to do it. Okay, fine. I'll tell you that some other time. So we discussed three important ideas today, slightly advanced ideas. This energy density in electric field is not advanced. This is basic only, half epsilon naught E square. We'll be using this a lot, especially in electromagnetic waves. Okay, electromagnetic wave is just a wave which creates electric field and magnetic field. If you know how much electric field and how much magnetic field it produces, you should be able to tell how much energy is propagating through that wave. Okay, energy intensity and all, they're all based on this. Okay, fine. We'll close this session here. Tomorrow we will start the next chapter. Moving charges and magnetism. Yeah. And to understand moving charges and magnetism comfortably, it will be better if you revise cross product of two vectors. Just how to calculate cross product and assign a direction to it. Revise that. It will be easy to understand what happens. Okay, thank you all. We'll continue in the next class.